Okay, this is a quick run through in last summer's Unit 2 physics exam on waves and electricity for the Edexcel International A-level. Okay, we're going to go through this as quickly as possible. This will allow people to prepare for their exam, Unit 2 exam, which is on Wednesday of this week. First question says, waves may spread out as they pass an object. Which is the name given to this process? Well, the answer is diffraction. So this is just something you need to know. Spreading out of waves is called diffraction. Okay. So A is the answer. Second question, what time period of a wave decreases? The time period of a wave decreases. Which properties of the wave increases? Well, frequency is inversely proportional to periods, so it's number 2, frequency. Next question, number 3, monochromatic light is incident upon a rectangular glass block. Some of the light is reflected and some of the light is refracted. Okay, so which property does not decrease when light is refracted? Well, the frequency stays the same. The intensity will go down because some of it's reflected. The speed decreases and the wavelength decreases. Okay, so the speed, you could say, decreases because the wavelength gets shorter, the wavefronts get closer together because they find it more difficult to get through the optically denser material. Number 4, current in a length of uniform wire is constant. Well, if the current is constant, they're just telling us which graph shows how PD, potential difference across the wire, varies with length. Well, we know the resistance of the wire is proportional to the length, and since they've told us the current is constant, that means V times IR. As the length gets bigger, the resistance gets bigger, so the potential difference will be proportional to length. So the voltage is proportional to the resistance of the wire. Okay, so as it gets longer, more voltage will be lost or used up across it. Question 5, an electron has a de Broglie wavelength as given 1.55. De Broglie is lambda equals h over p, where p is momentum, so it's h over mv, which gives the speed. So we want to change the subjective formula to make it v. If you follow my maths, you'll see v is h over lambda m, where m is the mass of the electron, which is given to you, h is given to you. So h has to be on top. The only one with h on top on its own is d. And if you check the other ones, this is the wavelength and this is the mass, so the answer is D. Question 6. 2 waves of wavelength 12 centimeters. They're giving us the wavelength. Leave a source in phase. The path, they travel along different paths to a specific point, x. The path difference at x is 18 centimeters, so path difference is 1.5 of the times the wavelength. So the phase difference, they want you to check now, the phase difference is out by half a wavelength because one has gone 1.5 wavelengths further than the other. So the difference, one wavelength will be in phase, but 1.5 will be out by half a wavelength. Half a wavelength is pi radians, which is 180 degrees, because a full wavelength is 360 degrees. The answer is C. Okay, 2 waves are coherent. That means same frequency of the constant phase relationship. So they're not always in antiphase with each other. They could be sometimes in antiphase, sometimes in phase. It depends on the situation. They have the same amplitude, not necessarily, but they must have the same frequency. Coherence means same frequency, more or less. Okay, that's question 7 done. Question 8, light from a laser incident on a diffraction grating causes a series of maxima and minima. So they've given you the first order where n equals 1. The equation for diffraction grating is n lambda is d sine theta. Okay, which of the following changes would decrease the distance between the central maxima and the first order? Okay, i.e. the angle decrease, so that means the angle goes down. At first I got it the wrong way around in my head, so it's very easy to misread questions. So you really, that's why I underline things. So here decrease is the key. So for theta to decrease, if you increase the distance from the laser to diffraction grating, it makes no difference. This is just a red herring. For those of you whose English is not the first language, red herring just means it's just there to put you off the trail. It's nothing to do with it, not applicable at all. Part number B says increase in distance from the diffraction grating to the screen. If you do that, they'll spread out more, not decrease. So theta will become bigger. Theta being this angle here, yeah, which you then use in the equation. If you use a diffraction grating with more lines per millimeter, that also causes it to spread out more. So these are two incorrect ones. But using a smaller wavelength, well, if lambda goes down, d is the same, n is the same, sine theta goes down, and sine theta is varies according to theta, okay? Because maximum 90 degrees sine theta will be at maximum, and 0 degrees will be at its minimum, okay? 9 is about intensity and power. So you've got Earth and Jupiter shown orbiting the Sun at different distances. Distances are given. And it then says the intensity of sunlight at Jupiter is Ij, so it's power over 4 pi. Distance of Jupiter from the Sun, I put it as R, could have put it as D. So this is the equation they want you to know. So if that's true, then the power of the Sun will be the intensity of each times the surface area. So if you imagine there's a sphere at this radius of the Earth, or the distance to the Earth, and there's a bigger sphere at Jupiter. Okay, so this is the area we're talking about. The area is 4 pi r squared. Okay, so it's the area of a sphere. Basically, is how much the light has spread out across that in 3D, so it'll be spherical. Okay, so like here's the Sun. At Earth distance, it will be a sphere of distance to the Earth, and Jupiter will be much bigger. Okay, so it's about 7.78 compared to 1.49, so it's 150 million kilometers to 780 million kilometers approximately. Okay, so when you do the math, so this is the intensity of Jupiter will be the power of the Sun, which is constant over 4 pi r squared. You can do a similar equation. So now we know the power of the Sun is the intensity of Jupiter, which is given to us algebraically, multiplied by 4 pi times the radius of the orbit of Jupiter squared. Okay, and for the Earth, it will be the same equation, except you replace it with 4 times pi radius of the Earth around the Sun. Okay, and then you divide one by the other, where you can replace the power in here rather than divide one by the other. Sometimes you do that. So you replace power with this equation, so you get the Jupiter values in there. The 4 pi's will then cancel out, and the ratios will be the 2 radii squared, okay, which gives you the answer A. So it's just a bit of algebra. If you can follow that, stop the video and see if it makes sense to you. And if you're doing A level, you should be able to do things like that. Okay, question 10, as the temperature of the filament in a bulb decreases, okay, again I was doing it the wrong way around, normally they go increase. If the filament of the bulb, the temperature decreases, the resistance decreases. Okay, this just changes, but we know it's going to decrease, which is the reason for this change. Okay, well, if the temperature decreases, lattice vibrations decrease and the resistance decreases. The answer is A. This is the opposite, and the number of conduction electrons do not change because these are metals. Yeah, it's a metal, so they're more or less the same. Okay, that's the multiple choice questions done. Okay, section B. This is part of an electric circuit, and it's just telling you in 60 seconds, so T is given. This many electrons pass point Z. Well, I is rate of change, flow of charge, and charge is the number of electrons times the charge of each electron, which is known. This is in the data sheet, so you could say its Q is N times E over T. Put the values in, you'll come to 1.3 amps approximately. It will give you value to 3 significant figures of 1.28, and that is approximately, as they've asked, 1.3 amps to 2 significant figures. Then they continue with the same kind of theme at the bottom of the page. In the same time, 60 seconds, the resistor transfers 24 joules of energy. Well, the equation is VIT. Since E equals VIT, you want to find out what is the potential difference. So that means potential difference is the 24 joules given divided by IT. IT we know from before, and the answer comes out to 0.31 volts. And you should keep the two significant figures there, okay? Because they've given you two significant figures, more or less. Okay, that's question 11 done. Question 12, investigating the internal resistance of a cell. This is a core practical, so you need to know the details of how to do this. So basically you measure the terminal potential difference of the cell. You have to measure the current. You vary the voltage and the current by an external resistor, in this case a variable resistor, which seems to be the most common way of doing it in this syllabus. Okay, so basically you're varying the resistance, and that varies the voltage against current. They're giving you data from 0.2 volts all the way to 1.6, and they're going to ask you to work out what the EMF is. So the EMF is the voltage when the current is 0. Well, the current is 0 here, so the EMF is the point, the intercept on the y-axis. Okay, and the internal resistance is the gradient of this graph, which would be negative because it's going downwards, so you can work out the internal resistance. I've used the values at 1.20 because it gives you an easy to read value on the y scale, and this value here is approximately 1.50 volts, as you can see. So basically extrapolate the line all the way to the y-axis, and this is what they're going to ask you in the next question. And I've then worked out the gradient for the internal resistance, and that's basically what they want you to do. They want you to determine the EMF of the cell and the internal resistance. So as I showed you, the y-intercept is the EMF, okay? By extrapolating means drawing the line beyond the point that they gave you to the intercept, and the resistance is the gradient of the graph. Whenever they give you resistance to calculate on the graph, make sure you show your triangle on the graph, okay? That's the marking point often. So I always put my data there. You can show your calculation here if you wish, but you might as well do it on the graph and then just say C graph. Comes to a value of 0.75 ohms, and you just put the values in. Don't forget the units. I had a student whose paper I was marking today, and she lost several marks because she kept putting the numbers in without the units, okay? Okay, so the student then placed an identical cell in series. So you have two voltages identical in series, so the voltage is going to double. Okay, he connected the voltmeter across both cells and repeated the investigation. So obviously the EMF will double as well. The student plotted a new graph of these readings and described how the new graph is different. Well, if the EMF would be double, the y-intercept, describe. You don't have to explain it, but I am explaining it. The EMF would double, so the y-intercept would be twice as high. It was 1.5 volts there, so it's going to be 3 volts. And there's going to be double the internal resistance as well, because they both will lose volts. So it's basically going to lose volts twice as fast, because each one of the internal resistances is going to lose the same voltage across it as the current also goes through the cell. So the resistance before was internal 0.75, so it'll be 1.5, but you don't need to calculate it. So the gradient of the new graph will be twice as steep, okay? As you increase the current, the voltage drop will be double, okay, for the same current. Okay, so for the same current axis, the drop in voltage will be double. So both of them double. So that's question 12. Question 13 is an observer showing a ray of light going from the fish to the eye of the observer. They're giving you the angles. The diagram is drawn to scale. They want you to use a protractor, to measure the angles, put the angles in, use the equation, to determine the refractive index of the water. Okay, so water is, I put it as N1 because the light's going this way, so N1 is water, sine theta is the angle in the water, N2 is outside the water, which is air. The refractive index for air is 1.00. and you put the values in, you'll get 1.33. Okay, so that gives you probably 1 mark for each line, 1 for measuring the angles perhaps. I'm not going to spend time going through the mark scheme right now. And that's the beginning of question 13. They've now drawn a different diagram. This time the light is reflecting off the sunlight, so it's going to be plane polarized. Remember, reflected rays are plane polarized. They want you to explain the difference between unpolarized and plane polarized light. The best way to describe these is with directions rather than planes, because planes are two-dimensional, directions are just up and down. Okay, so I would always stress to put that rather than the bracketed terms. The unpolarized light has vibrations or oscillations in all directions. Yeah, obviously the directions are perpendicular to the direction of wave travel or energy transfer. So this is the third mark that you have to get. So unpolarized light's basically the light is vibrating at all angles. It's not just always vibrating in the same direction. Whereas plane polarized light has vibrations in one plane or one direction only. Okay, so when they bounce up, it may only be going upwards and downwards. So basically, it gets rid of all of the various angles at which electromagnetic waves vibrate at. So you have to be able to picture this in your own mind. But basically, any electromagnetic waves doesn't constantly, the electric field isn't constantly going up and down. Sometimes it might be going up and down as the wave. So the wave's going into the page. So the wave could be going up and down as the wave's going into the page, or it could be that's at an angle, yeah, to the way I'm showing you, or it could be this angle. In fact, this has all of those various vibrations, and it just means unpolarized. Okay. So when it's polarized, it will only be in one up and down direction. So say it's going in there, it could be, for example, like this, yeah, as it's going into the eye. So make sure your notes are clear when you're revising. So you've only got till Wednesday to clarify all these points. Reducing the intensity of the reflected ray, it says, would help the observer see the fish. So how, explain how the observer can use a polarizing filter to reduce the intensity of light. Well, if he has a polarizing filter between the surface of the water and his eye, and he rotates the filter at various angles, so it is not aligned with the oscillations of the plane polarized reflected light, he can reduce the amount of light that would get through to his eyes. So basically the amount of light. And if he does it at 90 degrees, he can actually block off the polarized light altogether. So there's various ways of doing that. And if I wanted to show you the mark scheme just for this one, question 12, it's question 12? 13, I think. So question 13, B2. There you go. So there are some ors in there, which is why I'm showing you. So you can stop the video, freeze, and see how you've explained it, and how you may want to improve your communication skills on that question. Okay? So that's 11, 12, 13. Done. 14, I apologize. 14 is about an LDR and a fixed resistor in series. Okay? So it says, explain why the power dissipated by the whole circuit, okay, changes, yeah, as the intensity. I haven't told you which way it's going to change, so you've got to work it out. As the intensity of light coming in on the LDR increases. So if the intensity of light increases, the resistance of the LDR will decrease, so the total resistance of the circuit will decrease. Okay, so it says you should refer to why the resistance of the LDR changes as the light increases. So you've got to explain why. So if you haven't done the why, you might lose a mark. So they're telling you as light increases, so this doesn't get you a mark, but you then say the resistance of the LDR decreases, 1 mark. Why? So explain why, put these as bubbles, so these are the thinking bits. Yeah. Because of an increase in the number of conduction electrons. So by doing that, you're basically, the LDR is a material, semiconductor in nature, which when you shine light on it, the photons basically release more electrons, so more of them can conduct. That means, of course, that the current will increase. and the total resistance decreases. This is the same marking point, this sentence. Okay, looks like my red ink is running out a bit. The EMF of the circuit, however, hasn't changed, it's fixed. They haven't mentioned internal resistance, so you can probably assume it's negligible or can be ignored. Okay, so the EMF, they've mentioned that the EMF hasn't changed, so the total voltage is the same. But we know the current has increased, and since power is voltage times current, if the total voltage is fixed and the current increases, it follows that the power dissipated. So one is knowing that what the power is the equation to. You could do it by resistance as well. You could do, for example, V squared over R. But since I know the current's increased and the voltage is fixed, it's quicker to do it this way in the whole circuit. The power dissipated in the whole circuit because the current in the whole circuit has gone up. The voltage has stayed the same, so obviously P equals V times I will increase, and that's how you get the 6 marks. 1, 2, 3, 4, 5, 6. Hope that makes sense. Okay, that's question 14. I'm going to try and do this all in one go. Let's see if we can do it. Be a first time if I have. Question 15. Ultrasound can be used for checking cracks. Here's some cracks in the metal beam. Diagram is drawn to actual size. In other words, they want you to measure it for later on. The transducer emits a pulse. Yeah, the same transducer detects the pulse. Okay, if you remember GCSE, this happens when fishermen send pulses to see where the bottom of the sea is, or sometimes to check if they can find schools of fish, bounces off different materials. So the transducer detects a returning pulse from each crack. Explain why there is a returning pulse from crack B. Well, for it to get to crack B, it's got to go through crack A. Some of the pulse reflects at crack A, but not all of it. In all of these surfaces, there is some reflection and some transmission. Okay, so at crack A, but some gets through or refracts. And then again, some of the pulse reflects at crack B, so some of it will come back at crack B, so some will go this way and bounce back. Some will get through and bounce back, yeah, and ditto for crack C. Okay, so remember the distance traveled is there and back. Because, why does it happen? So explain why again. Because the density of the crack will differ from the metal, and that's what it detects, that difference in density, or the kind of change in the structure of the metal beam is what it's actually detecting. Okay, so for the density you could say the crack is a different material, if you like, or a different medium for the sound to travel through. So I haven't explained it properly because you didn't see my writing. I apologize for that because I'm in a rush. Okay, so hopefully you can stop the video, go through, I've already spoken it, and then you can check your own answers. So that's the beginning of question 15. Then it says one pulse returns 1.4 times 10 to the minus 5 seconds after being emitted. So remember the time is for to go there and back, 2x, and deduce whether the pulse was from crack A. The pulse has returned from crack A, B, and C. Remember the diagram is drawn to scale. You should take measurements from the diagram. The speed is 5,900 meters per second in the metal. The equation is 2x over t, the velocity. So we know the velocity, we know the time. All we got to do is work out x. You put the numbers in, you get to 0.041 meters. And then you measure that on the diagram, and this distance you'll find is closer to crack A. They say it's 4.1 centimeters. I measured it closer to 4.2 centimeters. Maybe it depends on the printer that's being used. Okay, then it says explain why ultrasound used to detect cracks in metal beams usually have high frequencies, megahertz rather than kilohertz. Well, a higher frequency, yeah, remember frequency is also proportional 1 over period, means the pulses of sound are much smaller, and that means also a lower wavelength. Okay, so smaller distances, smaller time periods, so a greater level of detail or resolution is possible with smaller waves and smaller periods, because if the pulses are shorter, it allows you to measure them with a little bit more detail. If the pulse is going on for too long, which is what a frequency is, it's a constant wave going through, then it'll be a fuzzier image, I should imagine. Okay, So remember, shorter pulses, smaller waves have more resolution. Okay, something to make sure you just remember for your exam. Question 16. Drivers use car headlights, obviously, to drive in dark. They emit light. Here's a graph of V against I's, the voltage current characteristics of a filament bulb. The headlight will only emit light, it says, when it receives at least 35 watts of power. Determine the minimum potential difference at which this will happen. Yeah. So use values from the graph. So I looked at it very quickly and I can see it's going to be around about here. Yeah. You put the values in at 8, it's insufficient power. If you do a quick calculation, you'll see it falls short of the 35. At 9, it's just over, so the minimum potential difference would be 9.0 on this graph. If you try 8.8, you'll see that it comes slightly underneath. So the answer is 9.0 volts. Okay, so that is the beginning of question 16. Then it says, in a car, 2 headlights are connected in parallel with a 12-volt battery. The battery has negligible internal resistance. In other words, they don't want to worry about internal resistance. Explain the advantages of connecting the headlight in parallel with the battery rather than a series. Well, of course, in a series, you only get 6 volts for each one because they share the voltage. So 12 volts is an advantage. You'll get brighter, more power. And the power is independent of each bulb. So if one bulb goes out, the other one will stay on. Whereas if you put them in series, one goes out, the other will go out as well. So you have no light at all. So you want most things in circuits to be in parallel. Okay. Here's the mark scheme, 16B part 1. So you can stop the video, and that's the verbalization of what I've just explained to you. Hope that makes sense. And you can see the rest of the question as well. So you can come back to this point in the video to have a look at the parts we haven't gone through yet. So that's question 16. Part B, part 2. Then the student has written the following hypothesis: when connected to the 12-volt battery, the combined resistance of 2 headlights in parallel, he says, will be 1/4 or is 1/4 of the combined resistance of 2 headlights in series. So the mistake I made was assuming the headlights in series got 12 volts each, but of course they don't, okay, because they're sharing the voltage. So you've got to deduce whether the student is correct or not. So your answer should include calculations using data from the graph. So you take the resistance at 12 from the graph. The value at 12 volts gives you a current of 4.6. You can work out the resistance at 12 volts. Do the resistors in parallel. You put them up and 2 significant figures. You'll see the total resistance in parallel gives you 1.3 ohms. So we now know half of what the student is saying. There's 1.3 ohms for a parallel. Resistors in series, the 2 resistors just simply add up. But this time for each headlight, they would only receive 6 volts. So you take from the graph at 6 volts, you get 3.2 amps. You'll find that to 2 significant figures is approximately 1.9 ohms. 2 resistors in series at that value will be 3.8 ohms. So that's approximately 3 times the value, because 1.3 times 3 is about 3. It's actually about 2.9 times. Yeah, 2.9 times. So the student is not correct. It's less than 4 times. It's about 2.9 times. Okay, so that's the mark scheme I showed you before. The next question, part C, it says the headlights are connected in the circuit using copper wire. The current in the copper wire is 4.60 amps, so the I is known. Calculate the drift velocity. This is the equation where drift velocity is V. Q we know is a charge of an electron. The number of charge carriers for copper has been given to you, so we know N. And Q we know. So the only thing we don't know is A, and they're giving you the resistivity of copper, and they're giving you the resistance per unit length of the copper wire as this value, which is R over L. You know from the resistivity equation that R equals rho L over A. Therefore, since we know rho, we know R, we know L from here, the only thing we don't know is A, put the values in. Well, this is R over L, but in the equation this way around, this is L over R. That means it's 1 over this value, so I've multiplied by 1 over this value. Okay, so there's the resistivity, and this is 1 over this. Okay, anyway, I'm sure you can follow it. It gives you a cross-sectional area of 9.83 times 10 to the minus 7. So now we know everything in this equation. Apart from V, we know I, we know N, we know A, and we know Q. So you change the subject of the equation around from here, you'll get the answers. You've got the current, this is the value to be done, and you'll get the drift velocity to 2 significant figures. Always put how many significant figures you're using in your final answer. Most of the values given are 2 to 3 significant figures, but so you could actually give it to 3 significant figures should you prefer to. Okay. All right, we've done this part. Question 16 is done. Question 17, there's only 18 questions, so this would be a record if we do it all in one video. Here's the energy levels of a hydrogen atom, down from 13.6 electron volts. Those doing chemistry will recognize that the minus 13.6 electron volts. To ionize it, you need to give them 13.6 electron volts. So this is called the ground state, the bottom level of the hydrogen. A photon interacts with the electron in the ground state. Okay, remember hydrogen only has one atom. It's an atom of one electron. So explain why this interaction causes an emission of another photon. Well, if the electron absorbs a photon, it absorbs a photon energy, and it will move to a higher energy level. So say it jumps from here to here, as an example. It's going to jump down. It will jump down again, and each time it jumps down, it gives off a photon of a known energy transition, and that energy transition will correspond to the frequency that it emits. So when it drops back down again to a lower level, it releases another electron. So there's an example I've given to you. It could also drop all the way back down again, which will give the same frequency that it absorbed. Okay, so that's 17. 17 part B is the photon has given a wavelength. We know the frequency therefore is c over lambda, and if you look in the mark scheme you'll be able to work it out. I just bypass that by changing the HF equation into hc over lambda, put the numbers in, I get the energy in joules. But we want it in electron volts, so to change from joules into electron volts, we have to divide the value of joules by the charge of an electron, and that gives you 5.70 electron volts. So 3 significant figures to 2 significant figures, you can quote it as 5.7. Okay, so we're talking about question 17. In question 17, it says, explain whether the atom of hydrogen could emit a photon with this energy. So no, the answer is no, because see the energy levels available in here. You have to work out all the possible energy transition, yeah, and you'll see none of them have a transition of 5.7 electron volts. It has to be the energy transition between two levels being exactly 5.7 electron volts. And here is the mark scheme, which you can look at. It's 17b part 2. Yeah, so here it is. If the energy transitions do not match, remember photons are quantized, so you have to take them or leave them as they are. If the energy of photon doesn't exactly match a transition in the electron levels, it will not take place. So now you can see the rest of the mark scheme as well for the rest of this question, which we haven't come to yet. Okay, so that's question 17. And the next part of the question, remember, photons are quantum levels, they're discrete energy packages. So the next one is to continue with this question. It says photons with energy of this much given, yeah, so 10 to the power minus 18 joules, are instantly on the surface of metal. That means it has a work function. The work function is given to you in joules. The metal surface releases electrons due to the photoelectric effect. That means the frequency of the photon is equal to the work function plus the maximum kinetic energy emitted of the electrons. They want you to calculate this V max value, possible speed, from this equation for the electrons. So we have everything. We know HF, we know this. The only thing we don't know is V max. So you take the difference between them. This is the energy difference between HF and phi. So that's how much kinetic energy you got. If you put the numbers in, then you square root it, you can get rid of that. V comes to 1.5 times 10 to the 6 meters per second. Okay? And then part 2 says, explain why the photoelectric effect demonstrates light behaving as a particle. Well, it has to behave as a particle because if it was a wave, a lower frequency could still release an electron, whereas in the quantum world, there is a minimum frequency to activate or release the electron. And below that, whatever you do, however much you increase the intensity, it won't happen. So you can look at the mark scheme that I put on the video for you earlier. You can freeze the video and have a look at it. So there is a minimum frequency needed to release an electron, which is equal to the photon package of energy. So this is each packet of energy. Each frequency is a certain size. Okay. The electron, which receives the minimum frequency, gets released immediately. There is no time delay. If it was a wave, it could just wait until it built up enough energy, and then the electron would accumulate over time and it would be released. Well, that doesn't happen. It either gets released or it doesn't, and it's an immediate effect. So this is a quantum or discrete packet of energy. So each photon, it says, interacts with one electron. Yeah? So this is 3 marks that I would get. I'd get 1 for saying this, 1 for saying this, and 1 for saying that. And if you look at the mark scheme, which I put for you earlier, there are alternative ways of getting the 3 marks. Please take a look. Okay, I think we're done. We're on to the last question. The last question is about a violin. A violin has 4 strings. Each string has a fixed position between the pegs at the end, which you tighten it so you put the tension on, and the bridge, which is here. At first I couldn't see the bridge, the line going through because of the photocopy. Okay, explain how a stationary wave forms. Well, the wave is reflected between the fixed positions, the peg and the bridge, and interference takes place between the waves going backwards and forwards. Basically, a stationary wave is a wave trapped between 2 fixed points called nodes, and the middle is the amplitude, where this is called the antinode. Okay, so here's an example of the simplest stationary wave you can have. Nodes at the end, so the peg and the bridge will be here, and in the middle it goes up and down. The wave can be formed on a string, the node at each end and the antinode as the center. The frequency of the wave is called the fundamental frequency. So the simplest form is the fundamental frequency. So you see this is half a wavelength. If you double it, you have to go to twice the distance off the page, and you will see that this is equal to half the wavelength. So this length that you could measure would be half the wavelength. That's a starting point. This fundamental frequency is given for the 4 strings in hertz. Okay, the tension of one of the strings, it says 71.5 newtons, and the length of the string is 32 centimeters. So immediately we know the wavelength. Okay, so, and they're giving us the mass per unit length of the string. Well, the equation that matches those is the speed of on the string is the tension divided by the mass per unit length of the string. It basically is how thick the string is, if you like, the density of the string, but per meter rather than per meter cubed. So you put the values in, 71.5 here, divided by the mass per unit length in kilograms per meter, and you get a value, and now you know the velocity. We know the wavelength, as I've shown you, is 0.64 meters, because it's 32 centimeters. You can then use the wave equation to work out the frequency being 293 hertz, where you'll see that's approximately equal to 294 for string 2, so it's approximately equal to string 2, and there is a penultimate part of this exam. You're over of this exam and you're onto the last page. The last page says the stationary wave on the string causes sound waves to be transmitted through the air. Okay? Describes the similarities, differences between stationary waves on the string and the sound waves transmitted through the air. Well, waves have the same frequency, so that's the sound you hear. So the frequency and period are interrelated, but the waves have different speeds because one is on a string and one is in air. They're in different media, different materials. Yeah? Remember, even in sound, the speed of sound in air is much slower than in water, whereas in air is 330 meters per second, in water is about 1600 meters per second, and in metals, as we saw before, is about 5000 plus. So sound waves transfer energy, but stationary waves do not. It's basically, this stationary wave is just a pattern set up between the 2 fixed points, which was the peg and the bridge. So stationary waves do not transfer energy, and sound waves, like other types of waves, are progressive waves. Okay, progressive versus stationary waves. So they want you to know that. 5 points they want you to know. Waves in the string are transverse in nature, sound waves are longitudinal. That's another difference you can talk about. And waves, and this is the final one, waves in the string have a varying amplitude at different points. Remember, the nodes don't vibrate, they're fixed points, whereas the antinodes between the center between the two nodes, you get the maximum amplitude. Whereas sound waves, all the points along the wave will have the same amplitude. And that ends this final run through before Wednesday's exam for you to compare your answers with my answers, which are based on the mark scheme and my ability to communicate. I hope you found this video useful. So good luck in your exam on Wednesday. We are now over 215 subscribers last time I checked. So we're getting a lot of people coming in and looking at our channel. The channel's new, it started in January, so thank you everyone who's been supporting us. Please like, share and subscribe. I did have a couple of people saying, why can't you send us a PDF? Well, I'm sorry, I'm too busy to send anyone PDFs. Why don't you copy it out? You must have a copy of the paper, and the fact that you copy it out will allow your brain to remember some of it, and it's a good form of revision. Okay, so I don't provide PDFs, but I have provided free of charge all of these answers and an explanation, which I hope is clear. So if you found this useful, please give me a thumbs up, okay? That's a like. Share it with your friends in your school. Someone to check with me to ask me where I was. He happened to be in the same country, and he must have noticed some of my other videos showing where I was. And I said, do people watch these videos? He said, yes, they generally watch them. But please share my videos with your friends if you're doing the same exam. Next year, I'll be moving on to the non-international Edexcel as well. So there'll be more videos coming up soon. Thanks very much. Hopefully see you in a future video. Bye for now. And good luck again on Wednesday.